see concept of error rate for binary phase shift gain, or I would say concept of bit error rate in general, and then evaluate the bit error rate for a particular scenario of BPSK. So what is bit error rate? So this is your transmitter. From here, we are getting the bit stream in the form of zeros and ones. So what will you do here? We will apply, if you remember the digital communication setup, here we have source, right? Then we convert the information of the source to the bit using source encoder. Then if required, we apply channel encoder. Channel encoder is the block which introduces redundancy, right? This we have discussed in short by example of repetition codes, right? And then this bits stream is converted to some form of waveforms, right? This is your transmitter. So once, for example, you are applying BPSK here, so 0 will be mapped with A cos 2 pi FCT, or in other words, A by K phi T, and 1 will be mapped with where phi T is K cos 2 pi FCT, right? This we have seen. 1 is mapped with, or you can put minus here, A cos 2 pi FCT, which is same as A by K phi T, right? So either this waveform will be transmitted over the channel, or this waveform will be transmitted over the channel. For the BPSK case, then what will happen? Some form of noise will change the transmitted signal, and we call that, we model this noise as additive white Gaussian noise, right? Then at the receiver, you will receive the signal immersed with noise signal. You call it XT. XT can be either this or this, depending upon the 0 or 1. And then you will receive XT plus NT. Then what will you do? If you remember, I told you, in general, you will see phi t. Phi t is the basis, right? Here only one basis, so only one phi t will be required. In general also I told you, right? If it is cos, it is sine, then this part will be 0, right? Just to make you recall this thing, right? This is a general transmitter, right? For the PSK and QM scheme. Correct? So here, since we are using BPSK, this part is 0. So I am not putting sine part, right? The quadrature, the lower branch, I am just not using because BPSK, and here only cos is used. So here, next what will happen? Integrate. So at the output we will receive, batao, plus minus A by K, because we will multiply, right? Plus some sample of the noise, right? W, where W is nt, it, dt, correct? So this we said is Gaussian with mean 0 and variance. Sigma square is equal to n naught by 2, where n naught by 2 n naught by 2 is the power spectral density of this white noise, right? Remember all of these things? I hope you remember. So what I said, by looking into this is your R, correct? Plus minus a by k plus W. So I also told you that geometrically you can see it like this. This is your transmit constellation diagram, and at the receiver what will happen? It will be, at the receiver you will get some this plus some noise, right? If you have transmitted 1, you will receive a by k plus some noise, right? So by observing this, I told you that you have to design a criteria. So what is the criteria? Minimum distance criteria, right? Since noise is AWGN, noise is AWGN, so maximum likelihood is same as minimum Euclidean distance decoder. It means whatever you receive, we measure its Euclidean distance from each point, and whichever is closer, we decide in favor of that. So for BPSK, this minimum Euclidean distance decoder is same as the threshold detector, and if R is greater than this point, which is midpoint of these two, we decide in favor of 1, otherwise 0. Yes or no? Because if your R lies here, it is closer to 1, closer to this, right? Closer to a by k, it means you decide in favor of 1, correct? यहाँ तक clear है? If noise is AWGN, your maximum likelihood decoder is minimum Euclidean distance decoder. It means whatever you receive vector, you have to calculate distance. So if your R lies here in this part, it is closer to 1, otherwise it is closer to 0. So accordingly, for BPSK, your MAD has become this, right? That you have to just see the threshold. Yes or no? So when error will happen? When error will happen? बताओ. When you have transmitted 1, for example, scenario 1, we have transmitted a by k, meaning corresponding to 1, right? But the received word R, which is a by k plus W, is less than 0. Yes or no? You have transmitted this, but the noise is added and noise take it to this point. It means if a by k plus W is less than 0, then error will happen, yes or no? Scenario 1. We have transmitted 1, but at the receiver, your R is less than 0. See, if R is less than 0, you decide in favor of 0, but you have transmitted 1. Yes or no? Is it clear? My point is, this is our threshold, right? If your R, what you receive is such that you have transmitted A by K, right? You have received A by K plus W. If A by K plus W is less than 0, then you will say you have made a mistake or you have made an error. Your receiver has made an error. scenario 1. Second, we have, you have to answer this. You have transmitted 0, meaning that minus a by k. You can also write cos 2 pi f c. I'm not, I don't want, because we are saying with respect to, everything is with respect to phi t, na? So no issue. This is the constellation point, and if you multiply with phi t, it becomes signal, right? The signal you transmit. Anyway, so the constellation point corresponding to logic 0 is minus a by k. So your received vector is minus a by k plus w, and if minus a by k plus w is greater than 0, it means you have decided in favor of 1, so you have made an error. Correct? Abhishek, yes or no? So there are only two scenarios when error will happen. Right? So what is the probability of error? But what would be the probability of error? This is your transmitter, this is your receiver. From here you are sending sequence of zeros and ones, and here after applying the threshold detector, you will get again sequence of zeros and ones. After this point, this is your R. Here you apply threshold detector, because we have seen that this is the threshold detector for BPSK. So error means, for example, from here you are sending 1000 bits. You at the receiver here, you just collect these 1000 bits and compare them. So number of errors. For example, out of these 1000 bits, 10 bits are not matching. That means number of errors are 10, and total is 1000. So what is the bit error rate or probability of error? 0.01. ठीक है अभिषेक? So this is the probability of error or bit error rate. इसको कहें नहीं. For example, 20 bits are not matching. This is the receiver, this is the transmitter. You are transmitting 1000, for example, or 10,000, and out of this 200 are not matching. Then what is the bit error rate? Then the bit error rate is 0.02. So depends, right? Depends, because here you are getting plus minus a by k w, right? So it will depend on the value of a and as well as the noise variance. If noise variance is very low, then your error will be less. If your A is very high, it means your symbol are far apart. If your A is high, for example, A is 2 and then A is 3, then it will become further away. So what will happen? You will need more noise in order to send this to this, right? This space. You understood my point? So bit error rate is depend on energy of symbols, because I told you the distance of this width from here is called energy, right? First, and also noise variance. Noise variance you can think as noise energy or the noise variance. ये समझ में आ रहा है कि नहीं? What is the probability of error? अभिषेक समझ में आ रहा है? At the transmitter, you have sent, for example, 10,000, 20,000 bits, and then at the receiver, after applying the decoder, you just save it and compare a number of bits at the number of bits which are, I mean, not same, divide by total number of bits is called probability of error, right? So this is the probability of error, or this is also called bit error rate. So for BPSK scenario, or you can see if you increase the value of A by K, or because K is constant A, then BR must decrease. If energy increases, BR must decrease. And what is the justification? Because the symbols becomes more and more separated, and therefore if we need more, I mean, because so we need more noise in order to take this symbol to this, right? Because what was the error? If you transmit this, noise should take it to this domain. Then only you will take decision in favor of this. Understood my point? Similarly, if your noise variance means if your receiver quality is good, if your noise is very less, then also BR should be less. Error should be less. If noise variance is less, error should be less. If energy is high, error should be less. Yes or no? So is there any formula for bit error rate of BPSK, or probability of error? Probability of error of BPSK? The answer is yes. We have just discussed two scenarios when BPSK will be in error. These two scenarios, right? So probability of error for BPSK is probability that R, probability that A by K plus W is less than 0, given you have transmitted 1 plus probability that A by K plus minus A by K plus W is greater than 0, probability you have transmitted 0. Yes or no? Just we have discussed two cases, this and this. पहला क्या था? Under the condition that we have transmitted 1, R is less than 0, we have transmitted 0, this is greater than 0. So this is the probability of error. I am not going to prove it, but I will give you the formula for this. This we can prove, derive. It is very easy to derive. If you want me to derive it, okay, quickly we do it. First, only this term, first term, probability and 0 and probability of 1 are equal, which is half. This is the probability that W is less than minus A by K. So W क्या है? W क्या है? W क्या है? Yes or no? W is a Gaussian random variable with mean 0 and variance sigma square. ठीक है ना? Just quickly I will tell you. If you want to know what is the probability that W is less than minus A by K, what you have to do? You have to integrate this PDF from minus infinity to minus a by k, this PDF we know, right? बताओ क्या था? Hmm? 1 upon root 2 pi sigma square exponential of minus w square by 2 sigma square. So you have to integrate this. ठीक है? क्या चीज? No, you don't need to integrate it. I will just give you the value of this. ठीक है? So there is no need to integrate. So I will just write the formula. For probability of error. But for the sake of completeness, I just did all of these things. The formula for probability of error of BPSK is half times this plus half times this, right? And this is the integral, right? If you call it I. So I. Similarly, for this case, the I will be this. In this case, you have to integrate. And what you will see, if you call it I1, that I and I1 are equal. Therefore, probability of error of BPSK will be same as this integral. This integral, right? This integral. So what is the answer? A by k to infinite. I will write this. 1 upon root 2 pi sigma square exponential of minus w square by 2 sigma square. ठीक है? So this is the probability of error of a BPSK signal. This integral is not possible to integrate. We cannot integrate this. So we have to take numerically. We have to solve it numerically. What do we mean by numerically? अभिषेक बताओ न्यूमेरिकली का क्या मतलब होता है? यहाँ पर इस फंक्शन की वैल्यू निकालो, छोटा सा रेक्टेंगल, right? There are various numerical methods to find the integral of a area under a curve. So what we are going to do, we call it Q function. क्या बोलते हैं इसको? We define a Q function because it is not possible to integrate such integrals. नहीं कर सकते ना, ये इंटीग्रेबल है नहीं, है ना? I mean, integrable है मतलब you cannot further reduce it to a closed form. So there is a Q function which is defined by the mathematicians, and there is a table which gives you the value of this Q function. What is T? QT. First understand QT means understand what is Q function and how it is different from this. If you put sigma is equal to 1, then it will become a Q function. ठीक है? Your integral of interest is this. Understood? But the mathematicians have defined Q functions like this, where QT means this is a standard Gaussian. This is called standard Gaussian. Why? Because its variance is 1. So this is the PDF of a standard Gaussian variable, and the tail probability of this is called Q function. So what is Q function? Tail probability of a standard Gaussian random variable. Tail. What is the physical significance of QT? Tail probability of a standard Gaussian random variable. Standard means variance is 1 and mean is 0. बोलो. So for example, T is 1. बेटा T probability होगी ना less than 1. This is not probability. What is the probability? इसका area under this curve is called Q function. हमें क्या चाहिए? हमें ये चाहिए. ठीक है ना? Just give me 2 minutes. Everything will be clear. We want this. We want this, right? So what we need to do, we will replace W by sigma with W. Then what will happen? बताओ मुझे. और W1 कर दो चलो. So dW will become sigma dW1. ठीक है. So dW I am writing sigma dW1. W by sigma is. ठीक है. यहाँ तक ठीक है कि नहीं? Is it okay? We are trying to evaluate the probability of error of BPSK, which is this integral. But I said that this integral we cannot evaluate because we cannot further simplify this. So what is given to us? Total the tail probability of a standard Gaussian random variable Qt is given, I said, and the table is available. So by using this table, you can evaluate the probability of error. So बताओ अभी क्या होगा? This sigma will cancel out. Yes, limit will be sigma W1. So your W is A by sigma. Okay. Just ask if you have any doubt. What we are doing, we are simply evaluating this integral by taking the help of this Q function. बस इतना कर रहे हैं हम, है ना? उसके लिए I am trying this I so that it becomes in the form of a Q function. Now this is my I and this is my Q function. Please ask if you have any doubt. So now, can you see these two? So my I, by looking at this, my I is same as Q function, and what is the T? A by K sigma. ठीक है? ठीक है यहाँ तक कि नहीं? Just look at this Q function. So if you replace T as A by K sigma, this your I will become Q function at A by K sigma. So my integral or probability of error of BSK is this. Yes or no? So as you can see, what is the, this is your Q function. You say something, if you increase T, Q will decrease or Q will increase? The Q function will decrease. Because if you increase T, the area will decrease and Q function is tail probability or the area of tail of a standard Gaussian random variable. So if you increase T, Q2 will decrease. Okay, it means my probability of error formula I have just evaluated. It says Q of A by K sigma square by sigma square. I have just to change it to sigma square, ठीक है ना? And sigma square is n naught by 2, which is power spectral density of noise. Anyways, so as I told you, if you increase sigma, what will happen? This whole term will decrease and Q will increase, therefore probability of error will increase. Yes or no? So if noise variance, if noise sigma square, if noise variance increases, probability of error increases, which is in sync with our intuition, where we said if our noise variance decreases, error decreases, or noise variance increases, error increases. Okay, Abhishek? So what we have done here, we have simply tried to evaluate bit error rate of a BPSK signal, which is this. Why it is this? We have discussed here, because error will happen when our A chi plus W is less than 0 given 1 was transmitted, or minus A by K plus W is greater than 0 given 0 was transmitted. So using this logic, we have tried to find out this, and since this and this are half, and also we have found out that this and this integral is same, so using Q function, we have found the closed form expression of probability of error in terms of Q function, and we have found first, if noise variance increases, probability of error decreases, or in other words, if noise variance decreases, this argument will increase, therefore Q function will increase and probability of error will increase. One second. If variance increases, this decreases. Yes. So argument will increase, and since Q is a decreasing function of its argument, Q is a decreasing function of T, right? Since T is this, and if you increase T, the area will decrease, therefore probability of error will decrease. Sigma square decreases, probability of error decreases. Now tell me, if A by K whole square increases, what will happen? बताओ. A by K square increases, argument increases. Argument increases, Q decreases, because Q is a decreasing function of its argument, and therefore probability of error decreases. So if you increase the energy, the probability of error decreases, which is in sync of our intuition that bit error rate must decrease if you increase the energy, and the reason was because the constellation points get separated. Average energy of BPSK A by K minus A by K energy is, I told you what is the energy? एनर्जी बताया था ना कैसे निकालना है. आई हैव ऑलरेडी डिस्कस्ड हाउ टू इवेल्युएट एवरेज एनर्जी ऑफ द कॉन्स्टेलेशन. एनर्जी ऑफ दिस इज डिस्टेंस स्क्वायर and half is the probability of this. So this is the A by K square is the average energy or the power, sorry, energy, that is better, energy. So sigma square is n naught by 2. A by K square is average energy of the constellation. So probability of error in other terms, you can write it. So in many places, in many books, you will also get this. ठीक है? Now it is clear, if you increase energy, probability of error will decrease. If you increase noise variance or not the power spectral density of the noise, probability of error will increase. This is the one concept which is called bit error rate. Concept of bit error rate we have discussed. Bit error rate means number of bits which are differ at the receiver end from the transmitter end divided by total number of transmitter bit, and we have also evaluated probability of error or bit error rate of BPSK signal. Please ask if you have any doubt. And in order to evaluate bit error rate, we have used the Q function, property of the Q function, because while evaluating the bit error rate, we were getting this type of integrals which cannot be further solved. So we have taken help from the Q function, and Q function is the tail probability of a standard Gaussian random variable. Standard Gaussian means mean 0 and variance 1, and this table is given to you. So let's take a question. If your E average by N naught is 10, what is the probability of error or bit error rate? Q root 2 into 20. Q into 10 means Q root 20. So this value will be given to you, so you can write point value this. If you plot it, it will look like this. EB by N naught in dB. dB पता है what is dB? Do you know what is dB? Decibel, right? Decibel. So EAV by N naught in linear, if it is X, then EAV by N naught in dB is 10 log 10 of X. ठीक है? So if it is X, the ratio of EAV by N naught is also known as energy to or signal to noise power ratio. Have you heard SNR? Have you heard the term SNR? Bolo? Okay, take a 5-minute break and let me know if you have any doubt. The assignment is just to plot this. Vary the value of EV by N naught in dB. Q function, you can find the value of Q function from your Python code easily. there is a command in that for different value of EAV by N naught, evaluate this, then take log of this values, whatever value you get. Okay, I will just explain in dB 0, 2, 4, 6, 8, 10. So EAV by N naught in linear will become 10 log 10 of, if it is x, call it x, 10 log 10 x. So you will get some values, put it here, q root 2 AV by N naught. So whatever value you get here, for example, this value is A. So q root A, then you take its log q root A, plot it in y axis. So for different values of this, you have to plot here. So here you will write EAV by N naught in dB, 0 dB, 2 dB, 4 dB, 8 dB, sorry, 6 dB, 8 dB, 10 dB, and the corresponding y will be this. You first evaluate, oh sorry, it's dB में है ना, it's my bad. Because it's already in dB, so linear में क्या हो जाएगा? EAV by N naught in dB is 10 log 10 EAV by N naught in linear. So EAV by N naught in linear is same as 10 to the power EAV by N naught in dB divided by 10. So here you will get 10 to the power x by 10. If it is 0, the value will be 1. 10 to the power 0 by 10 is 0. 10 to the power 0 is 1. So here you will get q root 1. Take its log, plot it here. It might value will come here, then here, then here, then here, and you will see this type of curve. ठीक है? Do you have any doubt in this table? Abhishek? This is clear, right? So what is not clear till now, please ask. हाँ? Q function का formula है. There is a command for Q function. You have to write. In MATLAB it is qfunc. I don't remember in Python. So there is a direct command. If, for example, you want to evaluate Q function at 2, so in MATLAB you just write qfunc 2. It will give. Yeah, in Python, correct. And that qfunc, what it does, this qfunc actually evaluate the tail probability of this standard Gaussian random variable from here to here numerically. So this is what this qfunc does. Okay, understood my point? This q function evaluate. What is the q function, right? We want to know this, right? Area under this curve, standard Gaussian random variable curve. So this qfunc, which is inbuilt function in MATLAB, does the same thing. You understood my point? Okay. In all the books, you will see the probability of error versus EB by N naught or EAV by N naught. Average EAV is the average energy of the constellation. N naught is the power spectral density. Though N naught by T. Okay. What is power spectral density? I am just repeating again. पावर स्पेक्ट्रल डेंसिटी क्या होता है? This is the power spectral density of the white noise. So white noise contains all the frequency components and this we call two-sided power spectral density. Why? Because it is also plotted in the minus frequency components. This is why it is called two-sided PST. So we have answered what is the bit error rate, number of mismatched bits between transmitter and receiver divided by total number of transmitted bits. This is number, right? This is number. Number of mismatched bits between transmitter and receiver, total number of transmit bits. This is called bit error rate. Then what is the bit error rate for BPSK? Whose constellation is this? E average is A square by K square. You can also write it like this. And we have found out for over AWGN with n naught by 2 with power spectral density n naught by 2, the bit error rate or probability of error is, but how Q function of 2e by n naught, EAV or E whatever by n naught. Clear है ये कि नहीं? Is it clear or not? Concept of bit error rate clear है? I'm just asking this. The concept of bit error. What is the error? Error clear है? What is the bit error? Bit error क्या है? You transmit 0, but at the receiver you decide in favor of 1. Or you transmit 1 and you decide in favor of 0. This is called bit error. And what is the bit error rate? For example, you 10,000 such bits and you see how many times I have taken the wrong decision. Divide by the total number of transmit bits. This is called bit error rate. Or yes or no? ये क्लियर है कि नहीं? बोलो भाई. नहीं है? Okay. And then we have evaluated bit error rate of BPSK over AWGN channel with power spectral density n naught by 2, and at the transmitter the average energy is E and the noise has power spectral density n naught by 2. So the probability of error or bit error rate is equal to Q function of root 2 E by n naught. Clear है? And in some books it is also written as Q2SNR, signal to noise power ratio. अभी क्लियर है यहाँ तक? Yes. So one more important concept is remaining. After that, we will stop. So take a 5 minute break and ask if you have any doubt. I have given one Google form where you can submit. Have you submitted? Yes. Oh, okay, it will do. No, I will just share one more. Yes, as far as I remember, for question 5, I have given Google form. Hmm. But it is okay, Abhishek. Just check it and try to do it in. No, for 5, I have created one Google form, which I have, the link is given in the Google Classroom. Please check. So quickly, we will just discuss one more concept. Okay, so this we have discussed for BPSK, right? This concept. If I ask you this question that now I am using constant, transmit zero, logic zero with no pulse or no signal, and one with some A normalized. What is this? What is this constellation? This is called on off keying. Which constellation is this? Bolo? This is called on off keying constellation. On off keying mod scheme, transmission scheme. Because when you want to transmit logic 0, your transmitter will be off, and when you want to transmit 1, we will transmit what? Logic 0 will be transmitted with no pulse, and logic 1 will be transmitted with APT, which I have also written as A by K, KPT, where KPT is phi t, and K is the normalizing factor, right? So that energy of this is 1. So what is if I transmit this constellation over, we are transmitting it over AWGN channel, and it is asked to design the receiver. How will you design the receiver? Again, you will do this. Yes. Then what will you do here? What will you get here? R is, बताओ क्या होगा यहाँ पर? Please switch off your microphone. This point. What will you receive at this point? Point A. What will be received at this point? Let's call it R. What will you receive? See, now I am trying to solve some numericals so that it helps you in the exam. Right? Receive signal after the correlator filter. This will be your correlator filter, yes or no? Because one dimensional constellation, only one phi t, only one filter will be there, correlator filter. Then you will integrate it after multiplying this received signal. So what will you get here? Xt plus nt. What is your xt? Your xt is this, depending upon your 0 and 1. Yes or no? बोलो भाई. यहाँ at the transmitter end, either you will transmit 0 or you will transmit this. At the receiver, this signal will be immersed with noise, and I am saying noise is same AWGN with power spectral density and not by 2. Okay? So what will you do at the receiver? You will apply this correlator filter. You will receive R. What will be the value of R? It will be either only noise sample or the A by K plus W. So if you have transmitted 0, you will receive this, or you will receive this. Either one of these two possibilities. Yes or no? Please think for 2 minutes and answer me. At receiver, we will receive, if you have used 0 means nothing, you have transmitted nothing, only noise. Otherwise this, where noise is this, right? And I told you, if this is a noise, white Gaussian noise with power spectral density and not by 2, this W is Gaussian with mean 0 and variance and not by 2. This proof we have not done, so just you have to remember this. टीवी होना चाहिए, बट ठीक है, इट्स ओके. अभी बताओ नेक्स्ट. So you will receive noise sample which is Gaussian. At the receiver, next you will receive R. Then what will you do? You have received some R. What will you do? But you will evaluate distance of your R with either this or this. So when you will decide in favor of one, when your R lies closer to this point, and the closure of this point is midpoint of this, which is A by 2K. Threshold is not always 0. The motivation of using this example is that the noise, you understood my point here, yes or no? So at the receiver, what will you do? Bolo. For example, your R is 0.4. A by K is 0.3. So here, what you have done, batao, you will compare whether your 0.4 is greater than 0.3 by 2 or less than 0.3 by 2. If it is greater than 0.3 by 2, you will say logic 1 was transmitted, otherwise logic 0. Okay? Now you have understood everything. How to design your receiver. What is the logic of designing your receiver? Maximum likelihood. But if your noise is AWGN, your maximum likelihood is same as minimum Euclidean distance decoder. ML becomes MED. What is the meaning of Euclidean distance? Decide in favor of the constellation point which is closer to the receive point. So if your receive point is R, so you have to check whether it is closer to 1 or closer to 0. So when it will be closer to 1, when it lies right to this line which is bifurcating, or which is just dividing this two in half, right? Dividing these two in half. So what is 0? It is A by K. A. You understood my point? So under AWDM, bolo? Yes. Okay, so there you are clear with everything, na? Okay, so I have taken a special example now that this is not BPSK, but this is on-off scheme. It is a binary signaling scheme, but it's not binary phase scheme because why it is not PSK? Because, bolo, and what is the average energy of this constellation? Average energy of this constellation is 0 into half plus a square by k square into half. So this is the average energy of this. Average energy of this constellation is, you have to evaluate distance of this with origin. This is itself origin. This is the A by K. So origin से distance 0, half plus A square plus K square into half. So average energy in this case is, okay, understood my point? So we have discussed beta rate specifically for this scenario where threshold was 0. Here threshold is this. If you want to evaluate error, you have to again repeat exercise, this exercise. Okay, थोड़ा सा different हो जाएगा. Here a by k plus w will be less than ak by 2. This 0, so a bit difference. You understood my point or not? Yes. Here the threshold is in the midpoint of the constellation for the maximum, like for AWGN, it is midpoint of the constellation. This is called minimum Euclidean distance decoder. Minimum Euclidean distance decoder. When your channel is AWGN, your maximum likelihood becomes MED. Okay, let me write a few points. Map is the decoder minimizes the error probability. So, in digital communication, we design map. ये क्लियर है? ये मैंने this we have discussed in the last class. Maximum is posterior probability receiver. When all constellation points are equiprobable, this we have discussed, map becomes ML. ठीक है? The second point is this. Third, when channel is, till now we have not discussed about channel, but now if your channel is AWGN, then your ML becomes minimum Euclidean distance decoder. Minimum Euclidean distance decoder, and you can for binary schemes you can get threshold between midpoint, or the threshold is midpoint of the constellation diagram. अभी क्लियर है? This is the whole journey. We have started with the concept that map is the decoder which minimizes the error probability. The proof we have not discussed. Then we have discussed and also proved that when all constellation points are equally probable, then map becomes maximum likelihood. And when channel is also AWGN, we have seen that maximum likelihood is same as minimum Euclidean distance decoder. So if there are only 2 points, you can always get a threshold easily, which is midpoint of these two constellation points. So this is the logic 1 corresponding. It contains it A1, A2. It is A1 plus A2 by. Now is it clear or not? ठीक है अभी? So this is the crux of what we have done in the last class and today's class till now. Okay, what is the one more? So error rate reflects the error performance reflects the reliability of a digital communication setup. Yes or no? बताओ. If out of 10,000 bits, only one bit is an error, you will say your setup is more reliable. But out of 10,000 bits, if 1,000 bits are in error, you will say your setup is not that reliable. Am I right? Am I making sense? What is the one more important metric which you usually hear when we talk about 3G, 4G, 5G, or any digital communication setup or broadband? One other important metric. This is the metric, error performance or bit error rate, which gives you how reliable your system is. But we are not discussing how fast your system is, right? Yes, very good. Capacity. There is one more important metric which we come across when we talk about digital communication. That is called its capacity, right? What is the capacity of? Since we are discussing only AWGN channel, let's first discuss what is the capacity of AWGN channel. What is the meaning of capacity? Capacity, right? Capacity C is the maximum value at which we can reliably transmit our information. What is the capacity? C is the maximum data rate or maximum data per channel use okay, so let's rephrase this sentence. So maximum rate in bits per channel use which we can reliably transmit. Maximum rate at which we can reliably transmit. So what is the meaning of reliably? Yes, reliably means with any desirable probability of error. As you said, though it is not technically correct, but it means, for example, you want to transmit 10,000 bits such that only one bit is in error. Also, sometimes you want to transmit 10,000 bits, but out of 10,000 bits, only zero point 0.1 bit is in error. Means 10 times 10,000 bits, only one bit is in error. 1,000 bits, one bit is in error. What is the bit error rate? 10 to the power minus 3, 10 to the power minus 4, and so on. You can get any desirable probability of error if your rate at which you are transmitting through the channel is less than the capacity. You understood my point? This is called Shannon's theorem, or channel capacity theorem, or coding theorem, or channel theorem. So Shannon's theorem is okay. So, so maximum rate at which we can reliably transmit. What is this unit? Though I am calling it bits, but it can be any. You can also use. Okay, so let it be bits. So bits channel use. What does it mean? It means in one channel use, what information you can transmit from source to destination, and if that rate is less than the value capacity, which is C, you can always get any error performance. You understood my point? Bolo, what is capacity? First of all, ठीक है, जिसने डिजिटल कम्युनिकेशन नहीं किया, दोज हु हैज नॉट डन दिस डिजिटल कम्युनिकेशन कोर्स, they will say capacity means, as one person just replied, data rate, right? Maximum data rate. But it is more than that. What is the technical definition? Shannon said, if you transmit your information less than capacity, then you can get any desirable error performance. So in one sentence, I have written very beautifully the maximum rate at which we can reliably transmit. This is called capacity. And the unit is bits per channel use. CU means channel use. Channel use means in one channel use, how many bits we can transmit. Okay. अभी उसका फार्मूला निकालते हैं. Shannon-Hartley theorem for AWGN channel evaluates the capacity in bits per channel use, and the value is half log to 1 plus, बोलो, ठीक है. P क्या है? बताओ. Shannon-Hartley theorem. This is called Shannon-Hartley formula for AWGN channel. क्या होगा बताओ? ये सुना है किसी ने? Have you heard this formula? This formula is very well known, right? We are not going to the proof yet. Okay. This is the capacity of the AWGN channel in bits per channel use. It means in one channel use you can transmit this much of bits. And not क्या है? Our spectral density of noise. What I said. This is the AWGN channel. And not by 2 is the power spectral density of the noise. Power spectral density beta. Power spectral density और okay not by 2 है ना. Noise power spectral density is given to us. Okay. Bit of. Give me 1 second. Because I have used power here, right? P. Okay, before this, let's discuss what is capacity. We have discussed capacity, how to evaluate capacity, how to evaluate. If X is the transmit signal and Y is the received signal, then there is a term which is called म्यूचुअल इंफॉर्मेशन. क्या होता है? म्यूचुअल इंफॉर्मेशन between x and y. This is your channel, this is your x, this is your y which you are receiving. This is called mutual information between x and y, and the capacity is maximum value of this mutual information. ये किसी को कुछ समझ में आ रहा है? Are you getting this or not? If no, just tell me. Hmm. 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 Hx is information in X, and now once you have received Y, what is the information in X remaining in X? So this much is the information about X which you have received. This is called mutual information. Hx क्या है? Total information in X. Hx given Y, after you have received Y, what is the information left in X? So Hx minus Hxy is this much you have extracted, right? So X you have transmitted, Y you have received. So Hx minus Hx given Y is the information which you have extracted. This is called mutual information. But this mutual information, if I write the formula, which I'm not going to write because I don't think that in one lecture we can do all of these things. So you can optimize this over the PDF of X, because X is a random variable and you can always optimize it over the PDF of X. So this is called the capacity. How can you evaluate capacity of any channel? This is the formula. Next, if our channel is AWGN and we apply this formula over the channel, we will get this value. Uh, yes. ठीक है. So let's take an example in order to understand this. Okay. As you said that this is the Shannon-Hartley theorem. And Shannon-Hartley theorem is for AWGN channel can be derived using this formula, which we are not going to discuss. We are just going to see the result. Write the expression for the capacity C. You can use your online tools in order to solve this of an AWGN channel bandwidth B, signal power E, and noise power spectral density and not by 2. क्या क्वेश्चन है? व्हाट इज द क्वेश्चन? Write the expression for the capacity of an AWGN channel with bandwidth B, signal power P, and noise power spectral density and not by 2. So capacity will be half log 2 1 plus P upon sigma square. What is sigma square for this case? The sigma square you will evaluate like this. I am not going into detail of everything here. Just I am telling you how to evaluate the values. So this capacity is in bits per channel use. Just read this statement. If you have a signal which occupies bandwidth B, then you have to sample it at twice its maximum bandwidth using Nyquist. If the duration of a signal, the signal is t seconds, how many samples will be required? Bolo? Okay, you are using Nyquist. Now is it clear? Now my voice is clear or not? Okay, so this is a very important topic and very important for exam point of view. So just ask if you have any doubt. First, what is this statement? There is a magical term, capacity, and Shannon said if you transmit less than that term, you can get any reliable communication. ये statement clear है? Okay, next. So the question is how to evaluate that magical term. See, so I have given the formula that it is the maximum of the mutual information between the transmit signal X and the received signal or yes, signal Y. And you have to maximize it over all the possible, because X is a random variable, all the possible input probability distribution. You have to maximize this I over all the possible input probability distribution. So this is the probability distribution. You have to maximize this term over all the possible distribution. Then you will get this magical term C. ये clear है? Is this point clear? बोलो. We are not going in detail. I am just giving you the formula. How will you get the formula? But it should be clear for you that if you want, how will you derive that using your books or etc. ठीक है? ये clear है कि नहीं? Input by changing the input probability distribution. Yes, correct. See, X is a random variable, right? What goes inside the channel will depend upon the here, right? What happens here? Can you control its probability distribution? If yes, then try to get the probability distribution which is closer to that probability distribution which maximizes this term. You understand my point? We will take an example maybe for the simpler case and then it will be clear to you. Okay? But before that, which is more important for exam point of view, let's discuss that. So if you apply this formula for the AWGN channel, the capacity comes out to be this. ये clear है? बोलो. ये formula clear है कि नहीं? See this numerical. ये numerical clear है? Is this numerical clear? Very important for the exam point of view. बोलो yes or no. Please read this, Abhishek. Abhishek, am I audible? But I think Abhishek is not present. Yeah, yeah, you are there. Just read out this numerical which says what write the expression of the capacity C of an AWGN channel where you are transmitting a signal with power P and the noise which is added in this channel has power spectral density n naught by 2 and the bandwidth over which you are transmitting the channel is transmitting the signal is B. You understood this? Okay. In that case, if you have understood this, the formula you will write is half log to 1 plus p by sigma square. ये clear है? And the unit is bits per channel use. It means in one channel use, you will transmit this many bits, which you can evaluate by applying this formula. But वो हम नहीं discuss कर रहे हैं. We assume that after applying this formula, we get this result for AWGN channel. And if time permits, we will see it. अभी ये clear है कि नहीं? बोलो भाई. Understood. So now the question is what is sigma square? Sigma square is power spectral density, two-sided power spectral density multiplied with the 2 times the bandwidth. Because this is your power spectral density, and if your signal is something like this, how much is the noise power in this domain? 2b multiplied by n naught by 2. So this is the noise variance or noise power. ये क्लियर हुआ कि नहीं? Yes or no? Okay. So this much of information you can transmit over AWGN channel in one channel use. Now go and read this statement line by line. This first. Just assume what is given to you that the bandwidth is B, right? Just assume that the duration of that signal is capital T. So if you want to transmit this signal of duration capital T and bandwidth B, how many total samples or how many total samples will be needed? Nyquist rate say we are sampling 2BT samples. 2B samples per second multiplied with this is your signal. The frequency, maximum frequency component of this signal is B. So we are transmitting at 2B samples per second. How many samples? 2BT samples. Total, how many samples? 2BT samples. So how many channel use will be required? Bolo? 2BT samples or 2BT channel use will be required in order to transmit this signal. But you said that using AWGN channel, in one channel use you can transmit half log to 1 plus p by sigma square. So total 2BT channel use, how many bits you can transmit? 2BT multiply कर दो, you will multiply with 2BT. So BT log to 1 plus. Yes, so BT log to 1 plus P by sigma square bits in T second you can transmit. Yes or no? You have a signal of duration T bandwidth B, so 2B samples per second, 2BT samples total. So in T seconds, you can transmit maximum this much of, in T second, this much of bits. So what is the capacity in bits per second? You have to divide it by T. So B log 2 1 plus P by sigma square in bits per second. You understood my point? So now, so if you solve the same question, so the capacity in bits per second is B log 2 1 plus P by sigma square, where sigma square is n naught by n naught into B in bits second, or capacity is half log 2 1 plus P by sigma square in bits per channel. But in many books or in many many videos, etc., you will see the capacity is B log to 1 plus P by sigma square. It means they are saying that in 1 second, how many bits you are can transmit max reliably. Right? Now you have understood these two. So if this is the case, if I ask one numerical to you that capacity, find out capacity of AWGN channel, bandwidth is 1 megahertz, you are using 1 megahertz of bandwidth, power at the transmitter is 10 power minus 3 watts, noise is, noise power spectral density is this. Evaluate the capacity in bits per second. If it is not given in the exam, just you have to derive in bits per second. What is the bits per second? P by n. Sigma square is n naught by n naught into B. बताओ 1 megahertz कितना है आंसर? So you can transmit 1 Mbps of data. Yes or no? Just confirm my calculation. I don't know if it is right or wrong. Hopefully it's right. Right? Just check it. Check. What are the example of AWGN channel? Tell me. This broadband or this you use or this ADCL wire you used, it is an example of AWGN channel. So there, if you want the capacity for this particular parameters, the capacity of the AWGN channel is my calculations right? Bits per second or 1 Mbps. This is how we evaluate the capacity of any channel. That 1 Mbps data rate, 2 Mbps data rate can be achieved. I'm not saying that what you are getting is 10 Mbps, but you can achieve this. You understood my point? This is the maximum achievable data. And Shannon said, if you transmit below this, you can get any reliable error performance. Please quickly solve this numerical, which is very important. And data rate gives you the idea about the data rate or speed of your transmission. Abhishek, am I audible? CUE channel use. Please let me know if you have any doubt. हाँ बोलो, प्लीज आस्क. ओके. हम्म. 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 No, this is not the bandwidth type. For example, let me first rephrase your question and let me know if I have understood your question right. This is user 1, this is user 2, this is user 3, right? Something like that you are asking? It might not be same. So you are saying that this user wants some rate, this user wants some rate, this user wants some rate, right? Is this the question you are asking? So first, how you are relocating various bandwidths to different users? This is your question? Is this your question? Yes. So first, let me rephrase your question and then I would answer. So what he is asking, he's saying that there are three users. So as you have applied this formula, how this formula is relevant for this scenario, right? Is this your question? Okay. So first, understood what is capacity. First of all, the capacity which we have discussed is the maximum data rate which you can achieve between the input and output, right? This is input, this is the output. So let's not make it wireless, just some source or something like that. So what is the maximum data rate which you can get through this channel? If this is an AWGN channel, the formula says that this is the maximum capacity of this channel. ठीक है? If the rate required is 2 Mbps and the transmitter has power of 1 milliwatt, what should be the minimum be? Right? Right? So let's try to understand it like this. He is asking, sir, this is the link, and he wants 2 Mbps of data, and at the transmitter, what are the two parameters which you can change, either power or bandwidth? If I say the transmitter has power of 1 milliwatt. The maximum power is 1 milliwatt. You cannot go above that. So what is the bandwidth I must use for this user, right? So just apply this formula. 2 Mbps and noise power spectral density is mostly fixed. So let's take it as 10 to the power minus 9, not as 10 to the power minus 9. If in the exam I ask this question, just clearly mention whether you are taking n naught as something or n naught by 2 as something, right? Anyways, so power is 1 milliwatt, noise is 10 to the power minus 9, noise not by n naught is this, so and the bandwidth required. Solve this 2 to the power 2 into 10 to the power 6. So it is not a very linear equation. What you have to do, you have to draw this with bandwidth, this b log to 1 plus p by n naught b, where p is 1 milliwatt and n naught is 10 to the power minus 9. Just draw this. Maybe you will get, I don't know, maybe this type of curve. So what is your requirement? Yeah, so if your requirement is 2 into 10 to the power 6, so what should be the value of P? So maybe here you can get 1.5 megahertz. Try to solve this, whatever, using this curve. Draw this curve. You understood my point? For different values of B's and the P which satisfies this, you stop there. You understood my point? This is how you can evaluate approximate B, which is will be required, minimum B, which will be required in order to get this rate. What I mean, am I have I understood your question right and answered it right? So yes. So this is the importance of this capacity theorem, and also if you fix your bandwidth, you can find out the power. What is the minimum power required if your bandwidth is fixed? You understood my point? What happens in general, bandwidth is fixed, that each operator or each user will get this much of bandwidth, something like that. But of course, you can use this formula and find out the parameters. Yes, you're right. Now is it clear? Okay. So first, we have not discussed this. We have to optimize this over all the possible input probability distribution. Okay, so before going to this, uh, what was the definition of the capacity? If the data rate at which you are transmitting is less than C, you can get any desirable probability of error. But how you can get that? You understood my point? AWGN channel है. This was our channel, for example. So We have evaluated the capacity, it is 1 Mbps. In our example, we have evaluated C as 1 Mbps. So if our data rate at which we are transmitting is less than C, the capacity theorem says that any probability of error is possible, where epsilon is very less. It might be 10 to the power minus 6, 10 to the power minus 10. Any probability of error is possible. Epsilon probability of error is possible. How? हमने तो क्या बोला था? That this is our transmitter. What we can do here? This is our source, the source encoder, channel encoder. Then bit constellation mapper, then channel, and this is the receiver. So this is our channel. This is whatever we are doing bit to constellation mapper. Here we apply the detector part. If you remember what will happen here, what will be the different blocks here? These are blocks, right? This. So after passing through this, threshold detector, for example, or okay, just write maximum likelihood. So here we will apply channel decoder. So what was the one example of channel encoder which we have used? Repetition encoder. Do you remember this or not? See, most of the content we have covered. Just I am, for the sake of completeness, we are discussing a few things. So just be a bit proactive so that you can understand everything. So first, what is capacity? Capacity is the term, and according to Shannon, if you transmit below this term, capacity, you can get any probability of error. But how? You have to do something at the transmitter end, right? What you will do? You will do channel encoding. What he said? He said, if your data rate is less than capacity, you have to find out a channel encoder-decoder pair. What he said? That you can get any probability of error. For example, I want 10 to the power minus 3 probability of error. He said that there will exist some channel encoder-decoder technique which will help you, or which can get you, or which will get you to this desirable error performance. Just you need to find out these two possible pairs. You understood my point? Have you understood my point or not? One example which we have discussed, that 0 will be transmitted through 000, 1 will be transmitted through 111, or 0 will be transmitted through like this, 1 will be transmitted through like this, and at the decoder you will apply majority decoder. Majority decoder means, for example, 010, one of the bit get flipped at the receiver. At the receiver you apply this complete setup. After threshold, your threshold says 010, but though you have made mistake of one bit, your majority decoder will say, no, you have only sent 0. So there is no error. You understood my point? Have you understood my point or not? I am just motivating you how are just trying to help you to appreciate the concept of channel encoder decoder by taking the example of the repetition code, and the channel decoder is majority decoder. There is a See, this is a very vast field of study, which is called channel coding or coding theory. And what coding theory says? Coding theory says find out ways. As Shannon said, there is a channel, okay? And as soon as you fix a channel, there is a magical term capacity C, which you can evaluate. For example, AWGN channel, and the term is magical term is 1 log 2 p by sigma square. Now the question is, if everybody says if R is less than C, you can get any probability of error. But how you can achieve it? So in order to achieve this, he said you have to try various channel encoder decoder schemes. One such scheme which I am trying to tell you is repetition coder and majority decoder, and I am telling you how it can improve the reliability. By improving the reliability means you are now getting closer and closer to the desirable error performance, right? For example, if you have not applied majority decode, the repetition code here, what will happen? Out of 3 bits, 1 bit will be in error, right? But as you have applied channel encoder decoder, you can see that you can correct the error. There are various schemes, channel encoding decoding schemes are available under the umbrella of, I would say, there are various schemes, block quotes, or you will say memoryless with memory. So under this comes convolution quotes, linear block quotes, and repetition code is the one example of linear block code. So there are various other codes, encoders, Hamming code. So various or different researchers tried different channel encoding decoding schemes in order to get the desirable error probability. For example, my channel, I have a channel, right, whose capacity is, and this channel has some parameter epsilon or some parameter delta. Okay, so now we can take this example. I have a channel which is binary symmetric channel. Till now we have seen AWGN channel. Now I am just trying to deviate a bit and introducing one more channel which is binary symmetric channel. Binary symmetric channel means you can, at the channel you can give either 0 or 1, and at the receiver you will get either 0 or 1. And there is a delta probability that 1 will be changed to 0 and 0 will be changed to 1. If you apply this formula here, see, there is no need to go in detail for this, but just I am trying to tell you all for the sake of completeness. The capacity of this channel is, this is called binary symmetric channel. For the course we have done, the capacity of this is 1 minus epsilon log 2 epsilon sorry, delta. So this is the formula for this channel. Just for this delta, if delta is the parameter, you can apply this formula, and we have found out that this is the capacity. If your delta is, for example, zero point 0.2, you will have some value, for example, maybe 0.6. So now, if your R is less than 0.6, so this is your channel, and what you are transmitting R, and the capacity is 0.6. So if you are transmitting less than 0.6, at the receiver you want probability of error of 10 to the power minus 3 or 10 to the power minus 4. So you have to use one of these various possible channel encoding scheme. Where will you use channel encoder? Here. And channel decoder here. And stop when you get this probability of. For a particular channel, you will find out a coding scheme which will give you desirable error probability. So we will say that these are the capacity achieving codes. Code for that channel. So as I said, different channel has a different capacity. So this is the capacity of binary symmetric channel. This was the capacity of the AWGN channel. This was the capacity of AWGN channel. What you have to do, you have to start researching or designing your codes, channel encoder decoder pairs, such that for that particular channel, it will always guarantee if you transmit below this value, it will give you any desirable error probability, and you will stop and you will say, I have found out the capacity achieving code for that. So this is a new branch of research that is called coding theory. So this was my aim to introduce you to the very nice mathematical field of or sub branch of communication that is called coding theory. Okay, have you understood up to this point? Course, what I am saying, the course is complete. We are just trying to fill the gaps for the completeness of this course. One more gap is, batao. Just I wanted to tell you that there are various other channels. See, there is a physical channel which you can map to binary symmetric channel. For example, take a CD drive. What is the CD drive? CD drive, you can save the data in the form of ones and zeros in various sectors, various bits. So what happens if you coat it with material? It might act as 1, and if you don't coat, it might act as 0 because you put a reader, right? Optical reader. If the material is present, there will be reflection. If there is no material, there will be no reflection. You understood my point? So CD drive, so what happens? You have saved 1 here, for example. But due to some scratch or something, that material get scratched. Right? So though we have wanted 1, but it will give you 0. Yes or no? So there will be a slight probability that when you have saved it at 0, but you will get 1. And it will depend upon the material of the CD. Right? And also with time, it will erode. So delta will increase. Understood my point? So what if You want to make the CD drive more robust or more reliable. What will you do? You can do one thing, that same one you can save at three places or three different places, right? And you can call majority decoding, no, sorry, repetition encoder. And at the receiver end, if these three, out of these three, two will give you one, you will say one. So there is less probability that all of these three will be eroded, right? So you can do it by any way, na. Once you can put generally the CD driver reads like this, na. So accordingly you can, according to the physics of the reading, you can do that, na. You can do. Just you have to make sure that how it reads and how it stores and then how it applies majority decoding, right? This mapping you should know. You understood my point? Just you have to make sure the locations of the point where you are doing this. Anyways, so what I said, there are various physical. So AWGN channel, what are the physical media? The wire channel. These wires you transmit information to computers, for example. That you can model using AWGN channel. You understood my point? So what is the capacity of this channel? Log to 1 plus P by sigma square. The question is how. So the question is, Shannon says that if you transmit less than this value, you can always get the reliable transmission. And for reliable transmission, you have to design your channel encoder decoder pair. And this study of this or this study comes under the umbrella of coding theory. You understood my point? So this comes under coding theory. Then only this part is left, source encoder. All of this we have discussed, right? So block of important block of digital communication setup is left, which we will discuss. This is your source. So I said the source encoder will gives you 0101 10 bit of stream bit, sorry, bit streams. Then we apply channel encoder in order to improve the reliability. Then this will add some bits to this information bit. This is called information bits. This is coded bits. Then you will map your bits to the waveform. You will transmit it. In the channel, something bad will happen. You will try to make maximum likelihood decoder. Before that, the what was the filter, right? Correlator filter or match filter, and there you will get channel decoder. Then inverse of this you have to apply. This part is left. This all we have seen how to use ML, maximum likelihood decoder, and for AWGN maximum likelihood is minimum Euclidean distance decoder, and how we do this mapping, bit to waveform mapping using Gram-Smith, etc. We have seen, right? Let us say we have a source which generates three symbols. For example, there is a person who always scheme three letters. But the probability of this is different. So this source generates it, okay. The probability of occurrence of A is 1 by 6, probability of occurrence of B is 1 by 6, and probability of occurrence of C is 2 by 3. Now your aim is to design a source encoder, because only until you do that you cannot transmit it, right? You need this mapping. So what we are assuming that our source is discrete. So there is a one scheme, Huffman. Okay. So for example, I map A with 0, 0, B with 0, 1, and C with 1, 0. So means 2 bits for A, 2 bits for B, and 2 bits for C. So what is the average length? What will be the average length? 2 into probability of A. Please let me know if there is some doubt. We are just quickly discussing the source encoder part. And what is the source encoder? The mapping of your input symbol to the bits. So average length is 2 into 1 by 2, 1 by 6 plus 2 into 1 by 6 plus 2 into 2 by 3. So the answer कितना होगा? Please tell me the answer quickly. Correct? Oh, sorry. So the answer is 2. So the average length is 2 bits per symbol. Message. Let's call it ABC as message. So you are using 2 bits per message. Okay. Another person. Better? No. It is a source encoder which is mapping A with 0, 0, B with 0, 1, and C with 1, 0. See, we have discussed PCM, right? Do you remember? That was analog source, and you are getting digital out, discrete out, 0, 1 output, right? So that is called analog source coding. But here, what we are saying, our source is discrete itself, and now we are doing its mapping to the bits. For example, typewriter. Typewriter gives you some alphabets, right? You type, yes or no? Do you know the Morse code? Have you heard the name Morse code? Dot, that, dot, this, right? Every English letter, what Morse did, mapped with the sequence of dot and dashes, right? This is something like that. Now you have a discrete, so the you have a discrete information source, means message symbols is discrete, and now you are going to map it with 0, 1, 1, 0, 0. ठीक है ना? What I am going to do here, I am saying that all symbols I am mapping like this, but another person comes, he maps A with 1, 1, sorry, for example, A I put here, C I put here. I map A with 1, 0, B with 1, 1, C with 0. So 2 bits for A, 2 bits for 1, C with 1. What is the average length? 2 into 1 by 6 plus 2 into 1 by 6 plus 1 is to 2 by 3. Tell me, what is the average length? Just quickly tell me. So 1 by 3 plus 1 by 3 plus 2 by 3, 4 by 3. So of course the average length of this is less as compared to this. Which one will you prefer? Tell me. Huh? Second one, right? Average length means what? What does average length signify physically? Physical significance. What is the physical significance of average length? It means, for example, this source which is generating ABC, 10,000 times it generates. You switch on this source 10,000 times. How many times it will generate one A approximately? Number of times A will be generated, number times B, number of times C. Batao. 10,000 multiplied with 1 by 6. 10,000 times multiplied with 1 by 6. 10,000 times multiplied with 2 by 3. Yes or no? And in the first scheme, you are mapping each symbol with 2 bits. So how many bits you have to use in order to represent this? A, 2, 2, 2. So total, how much space will be needed? Space or the memory will be needed to save this? This much bits. But in other scenario, in the second scenario, you will need 2, 2 and 1, right? Less space. So you are saying that you are more efficient way of representing the source which is generating ABC with probability 2 by 1 by 6, 1 by 6 and uh, 2 by 3, right? 2 by 3 is 2, right? So this is the more efficient. So we should move towards most efficient. What is the most efficient? Yes or no? This will be your question, no? The second is more efficient. So does there exists some other method which is more efficient? Which is more efficient? What is the most efficient? Right? So the answer is you should try to reach to the entropy of the source. And the entropy is defined, so L bar should be as close to L bar, the minimum L bar is the entropy. The entropy is probability of the symbol X. What is the entropy? One second. Entropies. Yes. So if this is set X, so X belong to set X. You understood my point? Is this formula clear to you or not? If X is a source, and the symbol, it generates symbol X, which comes from the set X. So you have to evaluate the entropy of this source. So what is the entropy of this source? 1 by 6 log 2 6 plus 1 by 6 log 2 of 6 plus 2 by 3 log 2 of 3 by 2. निकालो इसको प्लीज फास्ट. So what is the motivation? Motivation is to find out what is the minimum average length of any such mapping. What is the most or what is the minimum possible average length of any source encoder? Source encoder. We are discussing source encoder. So this is the source encoder 1. This is source encoder 2. What is the best source encoder? And the best means whose minimum length is least, right? The average length is least. So we should try to find out the source encoder who can give you average length close to the entropy. So what is the entropy of this source? So we have used this formula. Please tell me fast. Please tell me fast. Then we will discuss Huffman code and we will stop. Abhishek? Okay. What is the answer? What is the answer? Am I audible? कितना? 0.9. And what is 4 by 3? 1 point something, right? 1 point. Yeah. So the aim is to move closer and closer to the entropy. Huffman is the scientist derived a way which who came up Huffman came up with the algorithm such that L bar is close to the entropy. I'm not saying exactly equal, but it will give you the best possible L bar. So now let us take an example and Huffman algorithm will be discussed and then we will stop. So there are 5 symbols. So now my source, there is one more source which generates 5 symbols. And the probability of this 538 5 3 8 12 14 15. So okay, so it is 1 by 4. sorry, 1 by 8, 1 by 8, 1 by 4, 5 by 16, and 3 by 16. So there are 5 symbols. This source generates 5 symbols with this probability. So this is the probability of A, B, C, D, E. Now the question is how to map A, B, C, D, E with the sequence of bits. And we also want to make sure that it is close to the entropy. So first evaluate. Okay, let's see first the algorithm. So what you need to do, you need to sort these symbols with decreasing probability of occurrence. So first you will write the symbol which has maximum, the maximum probability of occurrence, then E, which has 3 by 16, then C, which is 4 by 16, B, which is 2 by 16, and then A, which is 2 by 16. So we have sorted or organized our input symbols in the decreasing order of probability of occurrence. Then what you have to do? You have to make a selection of two least symbols, symbols from the bottom, and you have to add the probability of occurrence of these two. Now again start the same. This is step 1. Repeat this step 1. Take two least probable symbols and sum their probability 8 by 16. Now 8 by 16 is the maximum. So write 8 by 16 at the top, 5 by 16 next, 3 by 16 next. Then again take the bottom two least the symbols 8 by 16, or you can because both are same 8 by 16, so let's do this. And you keep it. So problem यहाँ पर in this, one second, D is 5 by 16, E is 3 by 16, C is 4 by 16, B is 2 by 16, A is 2 by 16. Now we will add the two least occurring symbols. So 2 by 16 is 4 by 16, 4 by 16, 3 by 16. Then we will, हाँ क्या प्रॉब्लम है, ठीक तो है. हम्म हम्म करेक्ट करेक्ट करेक्ट. सी, understood. My bad. 4 by 16 should come. So now we have to do it again. So as rightly pointed out by someone, that we need to first arrange it in a decreasing order of probability of occurrence. 5 by 16, 4 by 16, 3 by 16, 2 by 16. 5 by 16 is D, 4 by 16 is C, 3 by 16 is E, 2 by 16 is B. And now you have to repeat, you have to take symbols with two symbols with least probability of occurrence, sum their probability of occurrence, make it a composite symbol, and the probability of occurrence is 4 by 16. So just put it here, 4 by 16. So 3 by 16 will come here, 5 by 16 will come here. will move there. So now again, quickly make this table of tree, horizontal tree, 7 by 16. So 7 by 16 will come here. 5 by 16 will come here. 4 by 16 will move here. 9 by 16. And you have to repeat these steps until the sum of the probability is 1. So once you are done, so once you get 1, you have to stop and you have to start numbering the branches like this. So this is the step 1, step 2, step 3, step 4. Now, if you want to encode your symbol D, what you have to do? You have to see this path. So, symbol D, only what are the two branches which comes in the path 0 and 0. So, D will be mapped with 0. Similarly, C, those who are from EC background, they are well aware of this. So, C, you will see 0. Uh, you can do that. You can either write 4 by 16 here. No. Mm-hmm. Hmm. In step 2, yes. Mm-hmm. No, no, no. The algorithm says that you need to take two least probable symbols. So, what are the two least probable symbols? This and this. Yeah. There is a logic, very simple logic behind that. Because which is most occurring, I mean, the symbol which is occurring most of the times, you will map it with less number of bits. Then your average length will be minimum. For example, A comes 10 times, B comes 2 times. So if you map A with single bit, your average length will be minimum, right? This is the logic of using this tree. Yeah, that you put the symbol which has high occurrence probability to the top, therefore the number of bits mapped to that will be less. We are not going in detail to that, but this is the logic. E में क्या होगा now? Now E, please map E. Just follow the path. Let me know if I am making any mistake. So 1, 1, right? Or am I making any mistake? 0, 1, 0, 0. So yes, one more thing, this will be the most significant bit. So if you are mapping B with this, so 0, 1, 0. So 0, 1, 0. So this will be most significant bit. So 0, 1, 1. No, no, no. Am I making many mistakes? 1 second. So most significant bit is this, right? 1. So 0, 1, right. So 0, 1, 1. So A will be mapped with 0. 0 will be written here. It is most significant bit. This will be most right bit will become the most significant bit. The rightmost bit will become the most significant bit. So 0, 1. Am I right? Gulshan, am I right? Okay. So now we are done with this course. There are various source coding schemes also. One scheme we have discussed, that is Huffman coding. So once you are done with this, you can evaluate its average length L bar. You can evaluate HX. You can evaluate its efficiency, which is HX by L bar. Step 4, you have to just the upper branch 0, 1, 0, 1, 0, 1, 0, 1. Now the next point is how to map zeros, the sequence of zeros, ones to each symbol. For example, you want to map A. So just follow the path. Start with A. This, 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 this. And see which branch it is coinciding with. So 1, 1. So the rightmost will become the most significant bit 0, 1. Understood? 0, 1, 1. 0, 1. Am I right, Gulshan? Gulshan is not present. Okay. So you can evaluate average length L bar because now you have mapping. You have the probabilities. You can evaluate average length. You can evaluate entropy. You can evaluate efficiency of this coding, efficiency of the source encoder. Yes, x is entropy of the source, which you have to evaluate from here. Entropy of the source. We have already discussed PCM, which is an analog source coding scheme. No, you should say that L bar should be closer to HX. As close as possible. So this is called source coding theorem. That what is the source coding theorem? That L bar for the lossless representation of discrete memoryless source L bar should be greater than HX. So this implies that L bar minimum is HX. Discrete, memoryless means from this source, if now A is coming out, at the next moment, what will come out is independent of whether previously A has come out or B has come out or C has come out. Means currently what will occur is independent of what has occurred previously, right? What has happened previously at time t minus does not change what is going to happen at t. You understood my point? At t, what would happen is independent of what has happened at t minus. This is called memoryless. So, you understood my point? Yes or no? See, when I write some definition, I have to be precise. That is why I write everything. That for discrete memoryless source, L bar is less than or equal to HX. Till now, whatever we were discussing was for memoryless source. But explicitly, I did not mention it. But it is also a DMS, discrete memoryless source. Everything we discussed till now, what for? DMS, discrete. ठीक है. What is the block diagram of digital communication system? Source encoder, done. Channel encoder, done. Partially though. Now bit to waveform mapper, done. This is the transmitter. What is the use of source encoder block? To represent your source. No. To represent your source. Efficient representation of the source in form of bits. In our case, now we have discussed in form of bits, sequence of zeros and ones. Channel encoder introduces some redundant bits intelligently. Yes or no? Right? Example, for example, what are the example? Huffman intelligently to make system more reliable, to reduce the error probability. Now you know this bit to waveform mapper. Now we have intangible form of information. Now, in order to transmit those bits, we need some waveforms, right? Depending upon the channel. For example, channel is optical. Then what will you do? You will map 0 with on, LED off, 1 with LED on, for example. Or your channel is RF, then you will transmit 0 with cos 2 pi of CT, 1 with minus cos 2 pi of CT, BTSC. So this bit to waveform mapping would depend upon the channel over which you want to transmit the information. Mostly, right? Then at the output of the receiver, we have mostly discussed that the channel is AWGN, even though, so this is the correlator mapper. Then we will integrate whatever we get. What will you apply? Maximum likelihood decoder, right? Then, of course, channel decoder. And if your channel encoder, for example, is repetition code, then your channel decoder will be majority decoder. Channel decoder. Then, of course, for example, you have applied this type of encoding schemes. A is mapped to D is mapped to 00, C is mapped to 10. So similarly, once you get sequence of bit, so source decoder, right, which will give you source output, right, at the sink. Whatever source is given here, source for example was A, B, C, D, E, for example, a particular case, and you have applied Huffman here, so you will get the corresponding bit streams according to these mappings. Then for example, I said that we will apply some kind of channel encoding, then we will transmit it through the BPSK channel, for example. We will do this, maximum likelihood will become maximum Euclidean distance, the sequence of bits will come out, the channel decoder will apply majority decoding or some other decoding scheme, and then according to this encoding, you will convert your sequence to the information symbols. ठीक है, now the whole digital communication setup is